Okay, in this section we're going to talk about power series in general. Those power series we looked at in 11.8 all came from the geometric power series. In general, power series don't all look like that, and we're going to have to use the ratio test to determine the interval of convergence. So here's an example of a power series that you can't evaluate the interval of convergence using the geometric formula. This would be called a power series in X because you have powers of X. And in general, you could have a this would be power series in X equal A. Or you could say power series powers of X minus A instead of powers of X. So this would be the more general power series. Okay, so the question in this section is, if you're given a power series, find which values of X the power series converges, and we're going to call it the interval of convergence. So like I said, we're going to use the ratio test on all these because these aren't geometric power series. You take the limit as n goes to infinity of the absolute value of a sub n over absolute value of a sub n plus 1 over a sub n. In this case, this right here is absolute value of a sub n plus 1. This is actually the reciprocal of the absolute value of a sub n. So what you do now is you see this absolute value of x to the n plus 1, absolute value of x to the n. You're always going to be able to do this. You're always going to be able to cancel all of them except for one more power. You always going to have an absolute value of x or x minus a on the top. This becomes n squared plus 2n plus 2. This is n squared plus 1. So when you take the limit as n goes to infinity, it's pretty easy to see that this factor goes to 1, doesn't it? So you end up with this. The ratio test is going to show that it converges as long as this limit is less than 1. So that means in this case, the absolute value of x has to be less than 1, which means x is between negative 1 and 1. But like I said, the ratio test is inconclusive at the endpoints, so don't assume that it diverges there. There's lots of different things that can happen. What you have to do is you have to take that value, go back to the original power series, plug it in for x, and what you end up with is not a power series, it becomes an infinite series. Okay, so you can use all the techniques of infinite series that we talked about in chapter 11. When you plug in x equal 1, this power series becomes this power series, and it's not too hard to see that this if you use the limit comparison test with 1 over n squared, this power series the limit is going to be 1, and since it's greater than 0, and since this is a geometric p series, this is a convergent p series, that the series converges when x equals 1. Okay. Now, when x is negative 1, I should say the power series converges when x equals 1. Now, when x equals negative 1, you go back to the power series and you replace x with negative 1. So you get this. And it's not too hard to see that this infinite series is convergent. In fact, it's absolutely convergent. How do I know it's absolutely convergent? Didn't I just get through showing this converges? So this converges at negative 1 also. So the interval of convergence, the ratio test gives you the radius of convergence, but to find the actual interval, you have to check the endpoints using other tests than the ratio test. And in this case, it came out that it converged at both endpoints, so it's the closed interval from negative 1 to 1. Lots of different things can happen there. Okay, let's try another one. I'm going to do a couple, then I'll give you a bunch to try. How about that? All right, we're going to use the ratio test. Instead of writing the limit on every step, let me just take the look at the absolute value of an plus 1 over a sub n. And this is the absolute value of a sub n plus 1. This is the reciprocal of the absolute value of a sub n. So like I said, this would be a power series. You could say power series at x equal 2, or power series centered at 2, or powers of x minus 2. That's what we'd call this type of power series. When you simplify this part, you get absolute value of x minus 2, and then this becomes 3n minus 1 or 3n plus 2. Now when you take the limit as n goes to infinity, you can see what's going to happen. This is going to get close to 1, and you have 1 times the absolute value of x minus 2, and it's going to converge by the ratio test as long as that limit is less than 1. Which means x minus 2 is between negative 1 and 1, or that x is between 1 and 3. But we're not done yet. We have to check the endpoints separately. When you check 1, you go back to the power series, plug in 1, and you get an infinite series. Okay? And you can use the techniques that we've looked at. This looks like by the alternating series test. I'm going to jump right to that because it's an alternating series. The limit goes to 0, and they're monotonic decreasing. So this is, even though I would say it might be, this is conditionally convergent at x equal 1. That's all we need. It converges at 1. Now at 3, however, when you plug in 3 in for x here at the original power series, this becomes 1 inside the parentheses. So you just get this power series. And I think it's pretty easy to see this power series is divergent. You could realize that this is actually greater. This power, the term is greater than 1 over 3 to the n. And 1 over 3 to the n is basically 1/3 times the divergent harmonic series. So it diverges at 3, converges at 1. So the interval of convergence is actually closed on 1, open on 3. That happens a lot. All right, let's look at this one. So this one, we're going to use the ratio test and look at the absolute value of a sub n plus 1 over a sub n. So this right here, the numerator is absolute value a sub n plus 1. Denominator is absolute value a sub n. You could cancel the x plus 3's to the n plus 1 over x plus 3 to the n, and you get absolute value x plus 3 left. The n plus 1 to the n plus 1, I'm breaking off a factor of n plus 1, and I'm writing it as n plus 1 to the n over n to the n. Then you can group that factor like this, because I'm going to take the limit as n goes to infinity, right? So I have it n plus 1 over n to the n, which could be written as 1 plus 1 over n to the n. Why did I do that? Because when you take the limit as n goes to infinity, I recognize this factor is getting close to e, isn't it? This is getting close to e, this is getting close to infinity, and this stays fixed. X plus 3 in absolute value is not changing. So what can you tell me about the limit as n goes to infinity of a sub n plus 1 over a sub n, absolute value? It's going to be infinity. So your guess might be that the power series diverges for all x. And that's almost true. There's only one x value for which it converges, if you think about it. Can you think of a value of x that you could plug in here that would make this a convergent series? And the answer is yes. If you plug -3 in, every term would be 0, and clearly the infinite series of 0 would converge. So that's an example of a power series that only converges for one value of x. Let's do another one, and then I'll give, well, why don't you try this one on your own? Go ahead. See if you can find what's called the interval of convergence for this power series. Okay, for this one, you look at a sub n plus 1 over a sub n. This is a sub n plus 1. This is a sub n. This is the reciprocal of a sub n. So when you cancel the absolute value of x's, you have absolute value of x plus 1 to the n, absolute value of x to the n. I should have said absolute value of x to the n plus 1, absolute value of x to the n. So when you cancel, you have one absolute value of x left. This n plus 1 factorial, remember, you can break off this n plus 1 and call it times n factorial. So you cancel the n factorial, so you get this. What's the limit as n goes to infinity of this? Well, x is fixed, right? So as n goes to infinity, this expression actually gets close to 0. In other words, it's going to be less than 1. The limit of a sub n plus 1 over a sub n in absolute value is going to be less than 1 for all x. So this is a case where the interval of convergence is all real numbers. Anyways, so what we just demonstrated here is this. When you're trying to determine whether a power series, when you're trying to find the interval of convergence, let's say, there are three cases. It can converge only when x equals a number. That's going to be when the limit of a sub n plus 1 over a sub n is infinity, right? Or it converges for all x. That's when the limit is equal to 0. But usually, what happens most of the time is you get some interval of convergence. And when you get an actual interval, don't forget to check the endpoints. And you're going to have to use a test other than the ratio test as well. You can't use the ratio test because the test fails when the limit's 1, right? All right, so let me give you something to practice here. Try this one. Find the interval of convergence. Okay, the ratio test, you're going to look at a sub n plus 1 over a sub n absolute values. It actually simplifies, this is a sub n plus 1, this is a sub n. The x minus 1's cancel, you have an x minus 1 absolute value left. 2 to the n plus 1 over 2 to the n, you have a 2 left. You have an n plus 1, n plus 2. So when you take the limit, this should get close to 1, right? So your limit becomes this. And for it to be less than 1, when you divide by 1/2, absolute value x minus 1 must be less than 1/2. Did you get that? So when you solve it, you would make this x minus 1 between negative and 1/2 and half, add 1, and you get this. Did you remember to check the endpoints? You should have gotten that this series converges at 1/2. I believe you can apply the alternating series test here, right? You can apply the alternating series test here, so it converges at 1/2. At 3/2, it diverges because you don't have the alternating series. You just have 1 over n plus 1. So this is a case where you have closed on 1/2. Did you get that? Closed on 1/2, open on 3/2. All right, we got time for a couple more, it looks like. Try this one. Okay, if you look at the absolute value of a sub n plus 1 over a sub n, let's see, you get, this is a sub n plus 1 absolute value. This is the reciprocal of a sub n absolute value. You see what you get? You get the x plus 2 to the n plus 1 over x plus 2 to the n. You have one factor of x plus 2 in absolute value left. You have a 3 to the n plus 1. You have a 3 to the n. So you have a 3 on the bottom. You have an n on the bottom and an n plus 1 on the top. So this is what you end up with. When you take the limit as n goes to infinity, doesn't this factor get close to 1/3? Okay, so you get 1/3 there. And so we get that absolute value x plus 2 must be less than 3 by multiplying both sides by 3. You get that. So then you can break it up and say it's, well, you should say x plus 2 is between negative 3 and 3. When you add 2 to everything, negative 5 and 1. When I plugged in negative 5 into the actual power series, I got that we have, well, either way, I think it diverges because you have negative 1 to the n times n. The limit as n goes to infinity of this is of the absolute value is infinity. The nth term does not go to 0 on either one of these. So you should have got an open interval, negative 5 to 1. All right, I got time for 2 more, I think. Try this one. Hit the pause button and try this one. Okay, when you look at a sub n plus 1 over a sub n, this is a sub n plus 1, absolute value. This is the absolute value of a sub n. When you simplify it, you're going to have an absolute value of x left on top. You're going to have a 2 on the bottom, and you're going to have a ln of n and an ln of n plus 1. This is what you end up with, right? So when you take the limit, it looks like this. What's the limit as n goes to infinity of ln of n over ln of n plus 1? I believe you can probably use L'Hopital's rule. I believe this limit just gets close to, well, by L'Hopital's rule you get that, and that gets close to 1. So you should have just got an absolute value of x over 2 is less than 1, which turns out to be x is between negative 2 and 2. Now when you check the endpoints, I got that it actually converges at x equal 2. At the right endpoint, it converges by the alternating series test. You end up with this. But at the left endpoint, you just get 1 over ln of n. When you simplify it, you plug in a negative 2, and these become 2. This just becomes 2 to the n. So the whole thing reduces to 1 over ln of n, and you could use the limit comparison test with 1 over n to show that it diverges. So you should have gotten open on negative 2, close on 2. All right, this last one's kind of tricky. This one's kind of strange. So try this one on your own. I'll just let you try this one, and then I'm just going to show you the solution, and you can hit the pause button and see it, okay? Okay, I'll let you just look at this, but when you use the ratio test on this and you simplify it, this is a sub n plus 1, this is a sub n. See how you get 2n plus 3? It just becomes 2n plus, actually this becomes 2n plus 1 here, right? Well, it goes all the way up to 2n plus 1. The one before it is 2n minus 1. So look, this cancels with this, so you have a 2n plus 1 left. So this is what you should have gotten when you simplify this expression. When you take the limit as n goes to infinity, this is getting close to 1/2. So you should have gotten absolute value of x is less than 2, x is between negative 2 and 2, and then again I'll just let you check this out. If you look at the right end point, it diverges at 2 because when you plug in 2, it's kind of sneaky. It diverges at both of them actually, but when you plug in 2, I did something kind of sneaky. You may have to think about this. This is n factorial, this is 2 to the n. I multiplied each of these by 2. So you got this. If you look really closely, you can actually see the numerator is greater than the denominator. Each of these terms is greater than 1. The a sub n does not go to 0 on either of them. So the interval of convergence is open interval negative 2 to 2. All right, we'll see you next time. Bye-bye.